All right, you're good to go whenever.
All right, I'm AaronResearch, and this year's RET, I studied drilling fluids and their application in the oil fields and in geothermal, and that was at the Wells Construction Technology Center. And so kind of one of the things I was looking for is how does the advancement of drilling fluids or the study of drilling fluids actually relate to something that could be renewable, such as geothermal energy. And so I think that any kind of advancement in that drilling fluid technology or advancements in the oil field in general are applicable pretty much directly to renewable resources. So to start off, I just want to talk a little bit about what exactly drilling fluids are. They're a lot more nuanced and complex than I originally thought coming into this. I had no experience with these fluids at all, but they do have a lot of characteristics and properties that help actually allow us to do the oil drilling that we do. So from pulling the drill bit as you go down to blocking fissures and fractures down hole, and also carrying out cuttings to allow us to drill for long periods of time without having to take the drill out to clean it. So I want to talk a little bit about the components of it individually. There are a lot of ways you can divide up the actual components of drilling fluid. I chose to do it these 6 ways, with the base being water. I'm only talking about water-based muds at this time. Drilling fluids are also called drilling mud in the field. So we have water as the base, we have some kind of densifier, viscosifier, pH stabilizers, deflocculants, and loss circulation materials. The water is the oldest form of drilling fluid that we have. It helps cool off the drill, help pull out the cuttings from the actual well site itself, and it's the base from which we're adding all of our different components and manipulating its characteristics. The density of the fluid is something we have to control, because the density of the fluid actually helps us control the pressure down well. Density is also called mud weight, but the pressure down hole helps us maintain a higher internal pressure within the well, so that none of the reservoir materials can actually invade that well and cause a blowout, and to keep that actual well site from collapsing in on itself. So we have to keep a large pressure down hole. We do that through manipulating the density or the mud weight of the fluid that we're using down hole. Viscosifiers help us control the flow of the fluid. So viscosity is the resistance to flow, and we need to have a good viscosity to actually allow us to carry up the particles from the well. So the higher the viscosity, the more fluid, or the more cuttings and materials you can carry upward. However, there is a trade-off. Viscosity that is too high will inhibit the actual rotation of the drill and can create a larger amount of gelling, which is, think of that as kind of it's almost a solidifying of the fluid itself. And when you have that happen, that can cause large pressure differences whenever you move the drill, causing an influx of fluids in the reservoir, or that cave-in or blowout that we saw with the low density. One of the main causes of pipe failure down hole is actually a low pH or a more acidic pH. We have to combat this with some kind of additive that will raise the pH or make it more basic or alkaline. Oftentimes that's something along the lines of caustic soda or perhaps lime. And we'll see in a second why caustic soda for renewables may not be quite as useful as the lime itself, but we need to maintain that with these pH stabilizers to prevent the actual hardware from being destroyed. Deflocculants are substances that help stop grouping of the minerals, or the additives. When you have a lot of those fluids down hole, they start to group together and create a flocculant or a flocculate. And that is they're grouping together, as you see in this example of this kind of clumpy mess, and that can interrupt the flow of the liquid, that can cause pressure differences, that can do all sorts of things. And so we add material like lignite to help break apart those flocculants, deflocculate the fluid, and keep that a more consistent fluid throughout. And one of the very, very important ones are these loss circulation materials, or LCMs. These are little particles that are able to go into fractures down hole or fissures or cracks and help seal those up and bridge them so that our fluids can actually continue to flow downward and not leave the well, losing the fluid and also dropping the pressure, or allow anything from that fracture to come into the actual well itself. We want to block out those little particles of various sizes, depending on the size of that fracture, to come in and plug that hole or bridge that hole, allowing us to have a more consistent flow of fluids. So all those work together to help us make a fluid or drill mud that is going to allow us to dig deeper and more consistently and keep those places safe for us. So the reason this ties into geothermal is for geothermal energy or renewable energies of this type, you will still have to go down underground. And from the given areas, a geothermal well is actually going to be most likely deeper than an oil well. You go deeper down to get that higher temperature to bring it up to create steam that will turn a turbine to produce energy. With that greater depth and that greater pressure, we see a much greater temperature as well. And that temperature causes some problems with these drilling muds. And so the reason that we see universities and other industries research this drilling mud is to make these muds more applicable to these kinds of environments. So we see at these high temperatures that dehydration can occur, so we have our water actually evaporating or leaving the mud or becoming too viscous. Certain lost circulation materials, if you're using something that's a bit, say, greener, fibrous, wood, things like that, those can get greater at that temperature and not plug the holes correctly or be too brittle to keep that hole plugged for a long time. And we also see that components that will stabilize the pH, like caustic soda, don't work at the extreme temperatures that we're seeing at that depth. And so we have other additives, perhaps like the lime, that could do the job. But those are things that we have to test in the lab to actually see how they work under those conditions. It's not just a lot of guesswork. Other areas of improvement that we see would be something like maybe more natural renewable additives or things that are maybe more locally sourced so that we can have a more, a less environmental impact on the actual, or less environmental impact because of the drilling mud. Some economic considerations or incentives, as it were, 15 to 30% of the drilling, somewhere in that range, that cost is associated with the drilling mud. So losing drilling mud down hole, having to import exotic additives and things like that, things that aren't ready at the site, those are all things that add to that cost. If we can bring that down, we can incentivize the private or governmental entities to maybe consider geothermal more seriously, more relevantly. One of the things that OU has been looking at, specifically at the Wells Construction Technology Center, is repurposing old wells, so wells that have stopped producing oil. Those wells, we've already got some of it dug up and ready to go, and they can plug, but they can open those back up and use those to actually start, kind of get a head start and actually start producing more geothermal energy from old well sites. Those well sites go from being just these abandoned areas to an actually beneficial production area. They have one currently in the works in Tuttle, and they're looking at some abandoned wells or plugged wells in Shawnee, Oklahoma as well. But you still need to have drilling fluid for those because the drilling fluid, again, maintains that well or that borehole down there. You can't just drill it and start pumping water. So they may have to take these to a deeper depth to actually reduce that geothermal, but in any instance, they'd still be using that drilling mud. Here's some of the things that I did in the lab this year. This year in the lab, I was able to mix some different mud samples and then test their density, compare that to what we calculated via a spreadsheet. They also put me to work attaching a flange to this pipe, and I'll talk about that in a second. That's another area of research that they're doing there that's really cool. But I got to get hands-on and see how they work, and you really get to see what's happening when these different substances are added, and you get to see that there's a lot more than just sticking whatever you can. It's not just the whole kitchen sink in the water, it's the order that it's added, the amount that's added, how long you mix it, how do you agitate it, how long can it rest, and things like that. So I density test, it's in loss circulation test, and also some viscosity tests, and things like that. This is the Excel sheet or spreadsheet that we made the first day, and this is, I'm sure Mike's seen with these before, but this is just something that we can use to calculate the masses necessary for these components. And there's all these little things that are happening from specific weights to different units and all these other things that we're going to have to calculate to make this mud a reality. Here's what the area of research that they were looking at. This is something that we, myself and Crystal, were able to construct. And this pipe setup is going to help them simulate an actual well site with concrete or cement inside of it. And what they're testing here is what kind of amount of gas is escaping from these wells. So let's say they have a well that's producing gas and oil. After it's been plugged and left behind, is there still gas that's able to come up in this pipe into our environment? There's leaking gas. There's nothing there to actually stop. Well, there's the concrete there to stop it, but the natural ground and earth is not there to stop it. So we have this pipe, and we're going to put concrete into that or cement into that, pump nitrogen into it to see what, if any, gas is escaping from this pipe and pipe setup. So there's other considerations thinking how to make these not only be used for geothermal but also more environmentally friendly in that regard, just stopping the escape of gas. And then it was a really good time just seeing all these things and learning all these different aspects of it. These are my citations, a lot of good research online and literature there for it. And these are my acknowledgments and thank yous for Dr. Slady, Crystal, Jeff, and Caesar helped tremendously in this. And the RT members, Dr. Hammond, Dr. Nancy, Tessman, and